Okay, I want to get a bit further, but I didn't. So for now, we're kind of close to our final aspects. Okay, so one of the challenges we figured out collectively was that 32-bit for an IP address is not enough, right? So that sounds like we agree on this somewhat. Yeah. So most IT professionals do that as well. So which is very sensible. So the idea was there in before that, but certainly standardization 1998 was to come up with IPv6 as a successor protocol.
Wow, 3.4 to 10 to the 38 addresses. That's a lot.
It's a lot, right? So it's written down here. Yeah, if you can read that, 304 to undecillion addresses or something. It's quite a bit. I have a nicer number later, I think. So it's a lot. It's a lot. Exactly. So the hypothetical idea was you can give every cent coin on the planet a unique IP address, right? So that's kind of the motivation behind it. So basically, this time we really don't run out of it. Yeah, so that's the kind of motivation. So we really want to get it right. So, and then consequence, of course, is that the IP address is considerably larger, right? So it's 128 bits, so quite a bit more. Doesn't look big, but as you figured out already, yeah, it's quite a difference, right? Having a few bits more makes a big difference. So, but unlike IPv4, the splitting becomes a bit easier because the idea is now, okay, we split it half-half. Half of it is network address, the other half is host address, right? That's basic interface ID. That's how they do it nowadays. Interface ID, because they also figured out that hosts can have more than one interface, right? So it's also a convention that has seeped in. That was okay in IPv4 as well, but you know, your host can have multiple network cards, basically. So they got away from the idea of identifying hosts, but identifying interfaces, in fact, more realistically. And oftentimes, yeah, so that's roughly the structure of the IPv6 address there. Space runs out, we figured that out, and that's pretty much it, exactly. So, but of course, since the representation in bits doesn't really help our case, we figured it out for 32-bit, it's not too readable. They don't do it for IPv6 addresses neither, so you see something like this. That's the hexadecimal representation. That's usually normative. So if you see an IP, let's see, there's some mumbling here and there. 10 more minutes, guys, then you have freedom. So if you see address structures like this, that is generally referring to IPv6 addresses. And instead of using the dot notation, they use the column notation, right? They're separated by column. And that's the idea. There's also some other ways of shortening it. For example, if your IP address only consists of zeros here or here on, you can just have two adjacent columns. And then those gaps are filled up automatically, right? Because it knows the number of bits that are necessary. So you can have much shorter representations. You find that sometimes as well, just to prepare you in case you see weird addresses with multiple columns adjacent to each other. Anyway, right? So, but anyway, the idea was here, okay, we have a massive amount of IP addresses, and I can't remember that number, and that's a good indicator for the fact that there is probably enough IP addresses. So, yeah. So the header, IPv4, 6, sorry. You saw the one from IPv4 before. I show you comparison in a second, but what's the most striking feature here, I think? What do you think is the most striking component of the the IPv6 packet now? If you look at size, for example.
It's twice as big.
It's exactly, it's twice the size now. If you recall, there was the original one has 20 bytes TCP without options, so we're ignoring options right now. And IPv6 has 40 now, and that's purely down to those two guys here, right? The source address and destination address. So it blew up the packet size, at least the header size, sorry, massively. So it affects which layer again? Which one?
The network.
That's the network layer, right? So this one, again, that relates only to a network layer to clarify this, right? Just the host-to-host communication. But it blew up massively, the header size that's associated with this. If you put them side by side, IPv4, IPv6, you see something like this, right? So it's pretty much only address and pretty much nothing else. What they did in order to compensate for it, well, they didn't compensate, but to, you know, alleviate this whole process is they threw out a lot of double checks and additional flags from IPv4 in IPv6. So for example, there's no checksum calculation anymore. The assumption is now that it's done both on lower level and on the higher level, which it's done. So on transport level, there needs to be some checksum calculation to verify that the package is consistent. But I actually don't do it here anymore because it would be just too much space consumption. So the header is actually way simpler. Only kept the essence, and other than that, it's pretty much only address. So it says something about a traffic class and flow level that is related to quality of service. So for example, if you have voice over IP data, like phone data, then of course you need to have a reasonably latency-free transmission. If it's something that can wait a bit longer, like email, for example, then you can indicate this in those headers there. So then the routers know, okay, those don't need to be delivered first. We can be a bit slower those ones. That was available before as a type of service header already, but not really systematically used. So yeah, so a lot of stuff has been thrown out to actually accommodate this. So that's the key idea here, key message I want to get across. So we're solving this by having IPv6. Routing gets kind of a bit simpler. The network versus host part of the address is fixed, and it's very likely that you guys can be dealing with actual public IP addresses on any sort of devices you're dealing with, right? How realistic that is another question, because the providers have interest for you not to run a web server on your mobile phone, right? For example, right? Because you're eating into their traffic, right? So unless there's a scheme for that one, otherwise I would open up port 80 on this device and surf my website from here. Well, why not, right? If you can. So there's some other constraints that may impinge on this, but from an addressing point of view, there should be no reason why you couldn't, at least when you use IPv6. Cool. All right, I leave it at that. About networking, it's a lot about subnetting that we talked about as well. I put the slides up there, of course, not necessarily strictly, but just some commands on Linux if you want to relate to it. One command is like super commonly used is ifconfig interface config. The default command you find on any distro is considered deprecated, it's the old one, but it still works. So I don't know, sometimes I like it, it's kind of fast to figure out the IP address, for example. So if you just run ifconfig, it will show you all the IP addresses that are of active network cards on your system with MAC address, IP address, and so on. It's good to look at. But the more modern command is IP. Just IP, and then you have different options with this. IP address to configure your address, IP link to configure, I think, things on the link layer. So the idea is that this command is able to configure on multiple layers of the network stack as opposed to just the IP address. But those would be commands to keep an eye on out on Linux. So it's quite handy. Good. The rest is quite straightforward. Oh yeah, just one word on ARP. What's ARP?
Address resolution protocol.
Okay, address resolution. Didn't we have DNS for that?
That is for link layer.
Okay. So what does it do? Just clarify it first, because we didn't talk about it, and it's not like super important, but it's kind of good to perhaps to know.
So basically, it maps like this. It maps between the MAC address, like the physical address of one device, and the IP address of it.
Yeah. Yeah, that's right. So when we talked about, at the beginning here today, we briefly talked about, so we didn't talk about bridges, right? So because bridges are, no one knows what they do anyway, so why bother with them, right? Well, you kind of should. So what bridges do, bridges still can identify MAC addresses in particular, right? So, and they operate precisely on the level that you were describing, because one of the challenges is, okay, if I assign my machine in Windows best, right, 192.168.1.1, how does the network actually know that I assigned it to my machine or to my particular interface? I configured it now, but how does the network know? Recall, what was the address on the lowest level that any network card has? Not you again.
The MAC address?
Yeah, media access control, right? So that's the lowest level address. And this one, does it need to be configured or not?
Well, you can in some cases, but no.
By default specification, it's a hardware address, right? It's built into your network card. So you kind of need to establish that link between that hardware built-in address, which kind of doesn't change, but possibly could change, whatever, and the software address, the IP address, which can change, at any given time. And that's the link here for this one is the ARP protocol. It's basically along the lines, the ARP protocol, and literally you should have a look, actually, open Wireshark and look for the ARP protocol and see what it does. It just tells who has IP address 192.168.1.1, right? And then the responsible network card that has been configured will send a response, it's me, my MAC address is. And then the sending party keeps a so-called ARP cache that basically maps the IP address to the corresponding MAC address. And that expires, so that ARP request is done repeatedly. And basically this is the way the address resolution works on a lower level. So if your machine actually within your network wants to communicate with another machine, it does so on using this mechanism, basically mapping your MAC address. And bridges the MAC addresses are only seen within a given network. So that's why the idea of collision domain. You don't want to, for example, if you send an ARP request out, it's pretty expensive on a networking side because it's a broadcast request. It goes to all hosts on your network. Imagine you have a rather large network. It means there's a lot of excess traffic, a lot of overhead for nothing, right? Because you are sending messages to 16.7 million machines, for example. Only one machine will write back, yeah, it's me. Okay. So it's not really an efficient way. So that's why there's bridges as well to minimize this kind of broadcasting traffic as well. Interesting fact. I saw that once having a overly rigid firewall setup. So someone thought, okay, let's get rid of all unnecessary protocols by configuration, and they switched off the ARP protocol. What do you think happened to that network?
Well, if you don't have any ARP resolution, and then you probably end up flooding the entire network with your traffic, because those switches can't actually, they can't map the MAC address to the...
Yep. So basically nothing happened anymore. Nothing, because no resolution was possible. No IP, no network stack was able to figure out what MAC address would correspond to what IP address, couldn't keep a cache anymore. You basically shut down the entire network, and the entire configuration, it was really a case, it looked really beautiful, right? Port forwarding and IP addresses set up properly, and it took me ages to figure out that this, the ARP was switched off, because that's a protocol you kind of never switch off, right? So it always needs to exist if you want to have communication on the network layer and upwards. So it's like, pretty much like I say, either you're flooding something, nothing happens, but mostly because something, no one is receiving it, right? Because you're blocking the transmission of it as well. So ARP is quite important, and it operates on between two layers technically. So because it links MAC address, which sits on a data link layer, and the IP address, which sits on a network layer. So it's a bit of a confusing setup there. Cool. Anyway, that's it for now. I wanted to talk about IaaS. Probably send it out as a video or do it on Tuesday. Sorry, probably as a video though, because I want to move on as well. Because I want you guys to get playing with OpenStack. And I'll let you know once I have something out there, then you can start exploring OpenStack, and you need to have that networking understanding at least to follow some of the instructions. There is a tutorial by EEC themselves. They're running OpenStack for us, and we're allowed to use it for the course. There's a tutorial that basically runs you through, but I still want you guys to understand what you're actually doing there when you're just following the wizard, which is really straightforward and kind of will work, but I still want you guys to get an understanding why you need to specify subnets and gateways and what that interface is and all what that kind of stuff all is. That's why this entire exercise here. Questions?
Just about Wireshark.
Yeah.
If you, for example, download the game, are you allowed to like sniff the packets that the game sends to and from the server, or?
So it boils down to technically which network you're on. So is it your home network you're on?
Yeah, for example, it's like.
I don't see any problem why you wouldn't be able to observe traffic within your own premises. So that's perfectly legal. It's like people coming out in of your house, you're kind of able to monitor them as well. So you shouldn't sniff on the public internet, but you're sniffing in your own home network, but it happens to receive packages that come from the internet, right?
Yeah.
So in this case, I strictly want to know what my Windows machine is sending over the internet, especially remember during the beginning when all the telemetry information came out. It was very sensible to actually explore what your machine is doing. My answer is clearly yes, right? Don't work on this network here, right? But if it's your home network, yes, sure. I would definitely have a look what's going on. I mean, you have very license to the game, and it's at least sensible to figure out, does the game first of all do what it's supposed to do, and does it, for example, send your data in an encrypted manner, right? Which is quite sensible. Sometimes quite surprising if you look at stuff, especially those IoT devices, they all still operate on HTTP. Everything is plain text. So, you know, it's a joke, you know, and you put username and passwords in there. So definitely. So yeah, but be mindful. And note that Wireshark is probably not one of the most dangerous tools because it's not intrusive. It just listens. But of course, be aware where you listen, what you listen, you know, and the sensitivity is good. The question is valid, of course. But don't use, you know, intrusive tools such as, you know, Nmap port scanning and things like this, because the alternative way, for example, to deal with this issue here, which is unfortunately commonly used but not necessarily desirable, is to actually scan off this host here of all possible open ports to see what services sit behind that network. Because it can give you a good attack angle, right? So for example, if you know, all right, on port 80 there's a version 2 Apache, right? With this particular version, you check the vulnerability list and you realize, okay, they didn't update this thing for like, you know, 2 years or so. Yeah. Then you kind of know the vulnerability you can actually use to infiltrate the network, right? So that's the kind of usual attack vector you could take, but don't, right? So this is, you know, on the dark side, and it's definitely not legal. So please don't use any tools like that, especially not without supervision or without instruction of the course or your company or, you know, or your occupation requiring it in any way. But if you do it, of course, for exercise purpose on your own machine, well, that's perfectly fine, as long, again, your network, right? So not on the public network. So it's clear to be about what traffic are you allowed to sniff and what information are you allowed to query. Yeah? Other thoughts? Not for now. Good. Then, yeah. So I'll send out a message once I have decided how to do it, either do a recording or do it in class on Tuesday. But the next topic we're talking about is actually going into OpenStack and setting it up. So I'll probably come up with a small tutorial to show you guys, okay, how to do it. So you have some running VM instance and you can see that it actually works. Did you guys all sign into OpenStack as I asked you last session? So at least just log in and log out. That's basically it, right? If you haven't, look at GitLab. There is under what they call it services section right now. There's a link to the OpenStack installations called SkyHigh here, and you should be able to just log in with your credentials, unique credentials. If you're sitting at home, you will first need to get into the VPN. There's also a link to the INSEAD page on how to set up the VPN to NTNU, but that's the only constraint you would have if you're working from home, basically.